Math 1314, Tyler Junior College, Section 3.6, Polynomial and Rational Inequalities. How to solve a polynomial inequality, example number 1. In the previous video, we made the transition from the graph of a function to solving an inequality involving that function if that inequality was comparing the function to 0. So greater than, less than, greater than or equal to, less than or equal to. But I kind of gave a couple of false impressions in that first video. Number 1, it is not required to sketch graphs to solve inequalities. The purpose of the graph was to motivate a plan of attack, which we'll summarize in a moment. And number 2, the inequality doesn't have to be compared to 0. That was just a simple way of representing all 4 possibilities: greater than, less than, greater than or equal to, less than or equal to. Now granted, this one is comparing to 0, and even if it wasn't, we could get it compared to 0 the same way we can get most equations equal to 0 by shoving everything over to one side. In fact, in part of this, we will get things equal to 0, but not as part of solving the inequality, but as part of solving an associated equation. So let's think about how to solve this based on the graph that we saw in the previous video. Visually, we're looking for where is a function's graph above or below the x-axis. That's why it was compared to 0, because above y is greater than 0, below y is less than 0. But actually, the technique doesn't require getting 0. Regardless, if we have the graph of a function and we're looking for the intervals that separate where the graph is above the x-axis from where the graph is below the x-axis, then the points that separate it are where the graph is on the x-axis, aka the x-intercepts, aka the zeros of the function, however you want to view it. So the first thing we have to do is figure out what makes this equal. So step number 1, solve the corresponding equation. Recall that an equation has an equal sign. This does not, at least not yet. So the first thing we're going to do is pretend it says equals and solve it. Now, how you solve that depends upon the caliber of the equation. This, of course, is just a quadratic equation. We'll be able to solve it fairly easily, even if that means using the quadratic formula. This one, however, we can factor. Again, I'm not sure where I got the 24 from. Maybe I should have left it there. I'm going to make a note to myself in the next, I'll tell you what would happen if we left it there, but let's do this one. This guy will factor. If you can find two numbers that multiply to give negative 60, but add to give negative 4. Two such numbers are negative 10 and positive 6. Those add and multiply correctly. So if we set each factor equal to 0, we get x equals 10, and we get x equals negative 6. Now be careful, this isn't the solution that we're looking for. These numbers happen to be solutions because they both make the equation equal to 0, and this inequality permits, this inequality permits it to be equal, but there are more numbers besides 10 and negative 6. The role of these two numbers is not to say we're done. These two numbers are what I will refer to as boundary points. Without getting into a rigid definition of what makes a point a boundary point, for our purposes, a boundary point is the beginning or end of an interval. Step 2, partition a number line into intervals at the boundary points. So we need to think about getting a number line and partitioning it at negative 6 and 10. To partition means to split into pieces that don't overlap, but together create the entire number line, loosely speaking. I say loosely speaking because we're going to imagine that we're removing the two boundary points and cutting this line into 3 intervals. The interval on the left of negative 6 is negative infinity, comma negative 6. Maybe you're wondering, should we use a bracket because it says less than or equal to? Well, right now we're imagining that we are removing these 2 points. So they're not there to serve as boundary points, endpoints. They're not there to be included in the intervals. At the end, we'll pass judgment on whether or not we want them, and that will be based on this inequality here. It wouldn't kill you if you put the brackets on them right now, but as a matter of consistency, I'm not going to. The next interval is negative 6, comma 10, and the final interval is 10, comma infinity. So snip, snip, cut the number line into intervals. If you recall in the previous video, on the graph, over each of the intervals that we had, the graph was either entirely above or entirely below the number line. We just got to figure out which one it is. In terms of this problem, that means that this interval either makes this positive or makes it negative. So we got to figure out which one it is. Same thing for this one, same thing for this one. If we know everything in a given interval makes the equation positive or negative, then we only have to test one value to figure out which one it is. So your third step is to select a test value from each interval. And I can tell you right now, this will have more than 4 steps. I'm not sure where I'll only put 4. So we need to pick a representative, if you will, a test value. So anything to the left of negative 6 would work here. Let's pick x equals negative 7. For the next one, anything between negative 6 and 10, let's pick x equals 0. Pick 0 when it's an option. And if it's not a boundary point, it will be an option in exactly one interval. And then a test value to the right of 10 might be 11. It really doesn't matter. I could have picked 1 billion or 900 or 17. Just as long as it's in the interval, it will suffice. The test values are called test values because you test them in the original inequality. Test each test value in the original inequality. Now, there are some teachers and professors that will advocate a different sort of path towards the end. This is the one that I choose. In case you're wondering, you don't actually test it in the inequality, you test it in each individual factor, but that's assuming the thing would factor in the first place. So I would rather show you the technique that always works instead of the technique that sometimes works. All right, so we're going to test each test value in the original inequality and pass judgment on whether the test value makes the inequality true or false. So let's test negative 7 in the original inequality by changing each x to negative 7. Be very careful with the negatives, especially when you have powers. So negative 7 squared minus 4 times negative 7 minus 60. I'm going to run out of room here, but we're checking to see if this is less than or equal to 0. So we got to work out the left side. This is 49 plus 28 minus 60, and we're checking to see if that's less than or equal to 0. 49 and 28 is 77. At this point, I can pass judgment. I don't need to finish 77 minus 60. The minute you know if it's true or false, pass judgment. 77 minus 60 is not less than 0, because 77 minus 60 is 17. This is false. And we have to check all of them. So x equals 0 will be easy. In fact, I'm gonna make up the room that I lost here with x equals 0. Because if I substitute 0 into the original inequality, I'll get 0 minus 60, which is negative 60. Negative 60 less than 0 is true. I can't help but to see a face here. Here's the 2 eyes, the nose, and the mouth. Put some marks on it. It almost kind of looks like Stewie with an earring. For the 11, same thing, substitute it into the original inequality. 11 squared minus 4 times 11 minus 60, less than or equal to 0. And again, we're trying to see if this is true or false. 11 squared is 121. 4 times 11 is 44. Let me combine the negatives. Negative 44 and negative 60 is negative 104, preceded by 121. I can pass judgment. 121 minus 104 is not less than or equal to 0. This is false. So test each value in the original inequality. Now, as a result of your tests, some of the values made the inequality true and some of them made it false. Your solution are the intervals whose test values made the inequality true. So now we're going to pass judgment on intervals. A test value that made the inequality false rejects the interval it came from. So the first and the last intervals are rejected. But a test value that makes the inequality true means that we keep that interval as part of our solution. I'm going to summarize step 5 over there between videos, but for clarity, I'm going to write it up here. Intervals whose test values make the inequality true. Interval whose test values make the inequality true are part of your solution, part of the solution. Use brackets and unions as necessary. The unions as necessary means that we could have had more than one interval in our solution, so at the end we would put a union symbol between them. Use brackets as necessary simply means do we include the boundary points? Recall that the boundary points make this equal to 0. This inequality said it's okay if it's equal to 0, so in this case we do include the boundary points. So our only surviving interval was negative 6 to 10, and because negative 6 and 10 make it equal, and our inequality allows that, we keep the negative 6 and 10, which means on their interval, we put brackets on them. Negative 6 comma 10 with brackets on both sides is the solution to the polynomial inequality. These are very straightforward. The hardest part is the first step, solving the corresponding equation, because how you solve that honestly depends on the magnitude of the problem.